Hi, everybody. This is Elizabeth Wilson from Dartmouth College. This is our new energy conversations with early career energy researchers. There's more people coming in to the presentation right now, so we'll give it about a minute and then we'll be starting at 6:03. This is a series sponsored by a bunch of different colleges, and we really appreciate having young researchers, postdocs, assistant professors from all kinds of institutions to really share their cutting edge work. And today we're really very excited to have Destenie Nock from Carnegie Mellon, and Paulina Jaramillo will be hosting this, moderating this session, and I'll be back at the end to tell you about the next events coming up. But if you have a question, as you remember, you can add into the Q&A box, and Stephanie will send it to Paulina to field at the end of the talk. So thank you, everybody, and we really look forward to the session.
Let me see how many people. Okay, I guess it's already 12:03, so we'll start. I'm happy to introduce today Destenie Nock. She's now an assistant professor in the Department of Engineering and Public Policy and the Department of Civil and Environmental Engineering at Carnegie Mellon University. She just started her official faculty position earlier this month, and we're super excited to have her in EPP. Destenie completed her PhD from the University of Maryland, University of Massachusetts Amherst last year in 2019. And since August of last year, she's been at CMU. Initially, she was a presidential postdoctoral fellow. Destenie works in the area of energy system modeling, has worked on issues of energy systems in North America, but also increasingly doing some work in Sub-Saharan Africa. She's very interested in equitable planning of infrastructure systems and energy systems, and we'll be talking today about her work. So without extending the introduction too much, I will let Destenie start her talk, and she can speak a little bit about her background as well. Thanks, Destenie.
Thanks, Paulina, and thank you so much for having me here today. So today I am going to talk to you about an in-depth analysis of greenhouse gas emissions and air pollutants from electric transmission distribution systems. And this work is on the newer side, and it's really focused on trying to take a more holistic approach to energy transitions. So the motivation for this work is the level of emissions in 2018 being very high from the electricity sector. We see about 27% of greenhouse gas emissions coming from the sector, according to the EPA. And this really results from 63% of electricity being generated by fossil fuels across the world. So when we're kind of looking at our transition, electricity sustainability can happen at multiple stages of our electric system. So first we have the power plant. So this is when we're thinking about shifting towards renewables, using more low carbon generators. Then we also have the consumer side. So this is when people are talking more about like deploying distributed storage, rooftop solar, electrification of plug-in electric vehicles. And then lastly, we have the electricity grid. And so this is going to be thinking about reducing transmission and distribution losses. In my previous work, I have focused on evaluating the sustainability of different power plant investments. So looking at the power plant level. And I just want to give you like a brief kind of flavor of what I have done in the past before I move into the new work. So I focused in New England because I went to school in Massachusetts, and many states in New England were talking about staying with the Paris Climate Change Agreement. And there were many questions in the region about what to do with the 5.5 gigawatts of coal and oil capacity that were at risk for retirement and what to replace that with. In addition, there was 3.3 gigawatts of nuclear that were also at risk for retirement as well. And one of the things that policymakers were asking is which combination of power plants is the most sustainable? So if we're going to have a power system with a mix of natural gas, hydro, solar, wind, oil, etc., then where would we best position ourselves moving forward as we transition towards high renewable futures and start to retire some of these plants? So answering this question turned out to be pretty complex because there's different generation capacity levels, there's different resource constraints, outages that you have, technical constraints on the grid. And so my original methodology was looking at inputting the hourly renewable resource demand and the initial generation capacity levels. We built an electricity model that evaluated the reliability of different mixes of power plants. And then this fed into a sustainability model, which you're going to see which you see in yellow, which calculated the sustainability metrics for the electricity contributions by power plant level. We established some preference scenarios that illustrated different stakeholders, so like an environmentalist versus an economist, for example. And then we ranked these portfolios based on those different preference scenarios. So some of key assumptions in the model were that it was a resource adequacy problem, meaning that we wanted to ensure the generation capacity was enough to satisfy demand. And we looked at it by abstracting from transmission constraints. And so this work actually doesn't take into account T&D losses. So we were just saying that the consumer's electricity demand in New England would be matched by all of the power plants within the region. This is a graph depicting how capacity translates into energy contribution. So on the x-axis, you have the different portfolios, which are just going to be the different mixes of power plants. And on the y-axis to the left-hand side, you have the capacity of each portfolio, which corresponds to the solid bars. And then on the right-hand side, you have the energy contribution. And so that's the result of our electricity model. And that's going to say, given the capacity that you have in the solid bars, how does this translate to energy contribution in the striped bars? And so you can see that there's varying levels of technologies. The green are offshore wind, brown's natural gas, blue is hydro, gray is oil, and red is nuclear. And so this model is really just going to facilitate the generation comparisons. So then this work feeds into a sustainability model where you identify different alternatives, which are those portfolios. You calculate the sustainability criteria. Step 2 is calculating the criteria scores based on that energy contribution projection. So the output of the electricity model. You normalize those scores between 0 and 1, and then you rank the alternatives based on the preference scenarios for representing the different decision makers. So of course, when we talk about sustainability, we have to talk what do we actually mean. And so here I was evaluating 7 different sustainability criteria. So first we have the economic side, so that's the levelized cost of electricity. And the environmental side, we have life cycle greenhouse gas emissions, life cycle air pollution, land use and water use. And then for the social side, we have fatalities and jobs per gigawatt hour. So this kind of gives you a sense about what the output of the sustainability model was. And on the y-axis, you have the different electricity portfolios, and on the x-axis, you have the sustainability score. So a longer bar indicates a higher score for sustainability. So just as an example for how to read this, in portfolio 9, this light gray bar corresponds to cost. So the lower the cost bar, the actually higher the cost because it's inversely proportional. So a lower cost is better. So that means that portfolios 4 cost is actually lower than portfolio 9's. So longer bars, higher sustainability. And so one of the things that we saw were that high levels of wind and nuclear in portfolios 4 and 9 actually helped shoot those ones to the top. And so the highest sustainability ranking of our top 6 portfolios all had high levels of offshore wind, indicating to the region that, regardless of what you care about, having offshore wind within your future scenarios would be very beneficial due to the low greenhouse gas emissions, air pollution, and the high number of jobs that you can create. Then at the bottom of these scores, we saw that retiring your nuclear plants early actually reduced your sustainability ranking, and that had to do a lot with the higher greenhouse gas emissions and air pollution associated with using more of the oil plants that were typically peaker plants, but would have moved to more of the base load status once nuclear had been retired. And then, so one of the things that we kind of viewed as a limitation in this work is that not all infrastructure was characterized in our sustainability assessments. So we had left out transmission and distribution infrastructure, and assuming zero losses in the infrastructure was actually leading us to have a lower bound on our generation capacity needs. Now we actually see that transmission and distribution infrastructure is left out of more than just my model. So in the Paris Climate Agreement, each country made nationally determined contributions, or NDCs, and these embody the efforts that each country has pledged to use to reduce the national emissions and adapt to the impacts of climate change. So the graph that you're seeing is on the y-axis, we have the emissions from the electricity generation in that country, and then on the x-axis, we have transmission and distribution losses as a percentage. And the green circles highlight countries that mention transmission and distribution losses in their original NDCs, and the gray circles are countries that do not mention it. So we find that only 32 countries mention grid efficiency and transmission distribution in their greenhouse mitigation strategies. In contrast to this, 110 countries mention some form of renewable energy. And so when we're kind of thinking about a sustainable energy transition, we need to kind of acknowledge that transmission and distribution infrastructure sustainability impacts are often overlooked. And this is going to impact how we build our grids. So if we don't include losses, this could actually lead to us overbuilding generation capacity. And so then instead of 1 or 2 wind turbines, maybe you're going to need to double it or triple it just to account for losses and inefficient systems. And this really comes from why do losses happen? And there's 2 types of transmission losses. So there's technical losses, and those occur due to physical limits, losses due to resistance, the composition of the material used or the type of metal. And then there's also non-technical losses. So that would be like when you think about stealing, fraud, inefficient billing or metering. And so then this is going to lead to compensatory generation, which are power plants that are required to generate more than 1 kilowatt hour to deliver a kilowatt hour to a consumer. So the guiding research question in this part of my work is, what are the emissions outcomes of reducing transmission and distribution losses? So this is the methodology that I am using to calculate the percent of losses within a region. And the percent of T&D losses, or NTD, is going to be equal to the reported T&D losses divided by the total electricity generation for each region. And then the compensatory generation for power plant G, so the extra generation that the power plant had to supply in order to compensate for these losses, is going to be equal to the percent of transmission losses times the generation for each power plant. In this line of the work, in previous work, I did 7 different sustainability metrics, and here right now I'm focusing just on environmental sustainability and specifically at avoiding excess air pollution. I'm just acknowledging that there are many facets to environmental sustainability, but you got to start somewhere. So previous work by my colleagues, Kavita Sarana and Sarah Jordan, looked at investigating the CO2 mitigation potential from reducing transmission and distribution losses. So this is actually one of their outputs, and they found a huge mitigation potential in China, India, the United States, and Russia. But one of the things that they did not take into account in their study was the impact of other air pollutants. And So that's where I'm coming in, because local pollution impacts are also important due to some of the health impacts that we see. So for example, with SOx, we see more frequent asthma attacks in people with asthma, and there's also exacerbation of cardiovascular disease. NOx can lead to increased susceptibility to lung infections and worsen symptoms of asthma, and also airway inflammation. And then PM 2.5 particularly can get into the lungs and the bloodstream, and there's really strong evidence that this can lead to adverse health effects. So then we also have to calculate the emissions. So I am using life cycle emissions estimations from the literature, and then my calculation for the air pollution emissions associated with T&D losses, or E loss, is going to be equal to the emissions factor, EF, so air pollution per unit of energy, multiplied by the compensatory generation resulting from the T&D losses, times the K factor. So the K factor is a scaling factor that I'm using to account for the efficiency of different power plants and how that differs in an actual country versus in the literature. And then I'm sourcing data from the International Energy Administration and the US Energy Information Administration. So I know I've enticed you guys about T&D losses. And so here is how the average percent of T&D losses varies by country. And so we're seeing that in the, like some of the ones I want to highlight are in China. In the US, we have really low, we have really high efficient systems. So China has 5%, the US is 6%. India is pretty high at 18%. And then in sub-Saharan Africa, we also see, well, actually just in Northern Africa and some sub-Saharan, we see higher losses. Now, this is going to translate to the compensatory generation. So inefficiencies do lead to overproduction. And so we see that, you know, although China and the US were very efficient at 5 and 6%, they have a very high level of losses at 381 terawatt hours for China. The US has 244 terawatt hours, and India, I mean, they have an inefficient system, but they also do produce a lot of electricity, and so we see them at 261 terawatt hours. And so then this, of course, leads to a high level of SOx emissions, and we kind of see in China and India, I mean, the bigger the circle, the more the SOx, in case that wasn't clear. And we see that here we can really focus on these three countries, and we're going to focus on these three countries in our analysis due to their high level of emissions, and understanding how the policies might change in efficient and inefficient systems. So here are two graphs that are showing the pollutant connection with the percent losses, so that's going to be on your left, and the actual T&D, like the magnitude of losses, which is on your right. So on the y-axis in both graphs, we have the log of the SOx emissions from compensatory generation, and then on the x-axis of the left graph, we have the percent of T&D losses, and on the x-axis of the right-hand graph, we have the magnitude of T&D losses. And so on the right-hand side, this is just to give you a sense about where some countries are. We don't see a clear link between emissions and percent of losses. And that's going to be due to the losses being more directly linked to the level of generation. And that's also just from the method that I'm using to calculate it. And then when we actually kind of translate this, moving to the right-hand side with where those countries are, we see that, you know, there's a clear relationship with the emissions, and this is going to kind of help us think through how should we really start targeting policies. And so, you know, having a transmission distribution efficiency policy in Haiti, for example, wouldn't have the same level of SOx emissions as an efficiency system in Iraq, for example. And so then, so the graphs that I had just shown you were using the average emissions estimations from the literature, but of course there are different ranges for different pollutants and different types of power plants. And so now I'm going to show a Monte Carlo assessment to capture that uncertainty. And Monte Carlo is just taking the probability distributions from the inputs and calculating how that actually translates to a probability distribution of the outputs. So just as a reminder, this is how I'm calculating the emissions. And then for my distribution assumptions, I'm assuming triangular distributions from the literature. And so that's going to be using the min, the max, and the median literature estimate. And then I simulate the Monte Carlo for 10,000 runs. And this is going to be a Monte Carlo that we created in Python. So here is the US, China, and India. And on top, we see the CO2 emissions. So the y-axis is actually the frequency, and the x-axis is going to be the grams of CO2 equivalent for 3 different countries. And then the one right below it is going to be the NOx emissions. And this is really to highlight how policies for CO2 emissions reductions might differ from policies for NOx emissions. So here we see that the US, I mean, it's actually skewed to the left in both cases, but in China and India, we have the CO2 emissions being skewed to the right and the NOx emissions being kind of skewed to the left. Now, I will point out that the CO2 emissions have like a tighter bound, even though they're larger, and the NOx have like a kind of a wider distribution. And so one of the things that we kind of see with this wide distribution are, well, where should we actually focus the policies if we're looking within the country? And so up until this point, the national policies that we've been kind of analyzing miss infrastructure at the subnational scale, which then kind of led me to do a deeper dive into the US. So here is the percent of T&D loss variation across the United States. And we see that losses tend to range between 2 and 5%, but in the Southwest Power Pool, for example, so Florida, Alabama, and some of the southern states, we see very high losses. We also see some high losses in the Midwest due to the space. And then that, of course, translates to a big magnitude in variation. And so even though Texas and California seem more efficient than some of our kind of northern Midwest states, that because they generate so much electricity, this actually corresponds to a high level of losses. So here is to give you like a sense about the spatial distribution of SOx. And so just like with the world level, we see that the overgeneration kind of hints at where our air pollution emissions are going to be. And we see like a really high level in California and Texas, just because, I mean, they produce so much energy, and they are 2 of the most populated states. And you could say, okay, well, this is an average, but what about the range of emission in those bounds? So here are pollutant ranges in the 5 most populated states for CO2 emissions on the top and NOx emissions on the bottom. And we see that in Texas and Florida, for example, I mean, their bounds are going to be above, well, most of their emissions are going to be above 0.5 grams of CO2 equivalent raised to the 10 to the 13. And then in the NOx emissions, like California continues to be skewed to the left-hand side, whereas Texas has like a wider swath. And so this is really going to kind of impact where the states are going to have to target their emissions, because Texas has more oil plants. That's the capital for ExxonMobil and a lot of the gas companies down there. Whereas like California, they're switching to renewables. And so then when we're thinking about T&D losses in California, it might be more beneficial to look at this in combination of reducing our need for investments in wind turbines, for example. So making sure we're not overbuilding or not having to overbuild our wind turbine capacity. And in Texas, reducing the T&D losses might just translate to helping us transition from fossil fuels by retiring some of those power plants. We also see how we can also see how the ranges change for SO2 emissions at the top and PM at the bottom. And so here, if we're going to focus on PM emissions, then we actually see that we would really focus our policies on Texas and Florida out of these 5 most populated states. And then if we're going to focus on SOx emissions, like California and New York are actually doing pretty okay. And so then it would really be thinking about what states are feeding into, or what generation from other states outside of these states is feeding into those states, or where is this generation flowing? So some of the conclusions from this quick dive into my work is that this work has investigated the air pollution emissions associated with transmission and distribution systems at the national and subnational scale. By addressing these T&D losses, we're not only going to reduce greenhouse gas emission and air pollutant emissions, but also low carbon investments would be protected from grid inefficiencies. Now, I want to acknowledge that the ability to reduce T&D losses will depend on the specific requirements of the country, the state of its infrastructure, and the structure of ownership and of its power sector. But through incorporating T&D investments into electricity planning, countries can identify the most cost-effective and sustainable local infrastructure solutions. So thank you very much for listening to my talk.
I don't know what you can see. Can you see me?
I can see you.
Okay. So now we're open up for questions. And while we wait for questions to come in, I will ask you a couple of questions.
Okay.
Some of them are, well, we start with some that are maybe a little bit more on the methods, and then I'll go, like, I have some questions about broader. So my question is about like the emission factors. I think you had slide 24 is where you had the equation, and it wasn't clear to me, like, so the emission factors, you say that in air pollution per unit of energy, is that per unit of input energy or per kilowatt hour of electricity?
Per kilowatt hour of electricity.
Okay, and so I'm a little confused about the scaling factor for efficiency of different power plants.
So that's to account for the emissions factor that I'm getting from the literature having like an assumed efficiency of that power plant. But then when I'm actually calculating, like in the US, for example, I take the EIA's data and they actually have like the input energy and then how much electricity they've gotten out. So then I calculate the efficiency of that specific power plant. And then I use the scaling factor to say, okay, well, if the efficiency from NREL study, for example, is like, 20%, and then the efficiency from the EIA's this specific power plant is 28%, then I divide one by the other to account for the emissions being slightly different.
Okay, so I guess these is emission factors at the power plant level. Right. So where do you get the power plant information for countries in sub-Saharan Africa? Like not just, well, the power plant information, both in what is the efficiency, but also what type of power plants they have.
So that's going to be a combination of using this site called EcoFIS, and I also use the International Energy Administration. So some power plants don't, like some countries don't actually have the efficiencies for all of their plants. Like we're working with India data to try to get their more specific changes, but I would do 130 countries. So we have been using the EcoFIS site for the countries that they have available, but if the country doesn't actually have like the efficiency ranking of their power plants, then we assume that it's equivalent to the literature in that case.
And so I guess a follow-up to that is the emission factor for the country. Is it weighted? Is it a weighted emission factor based on the output from the different types of power plants?
Yes. So it's like I have one for oil, one for natural gas, and then I combine them.
But it weighted by their output, right? So a country that has 80% generation from coal and 0% from renewables, like is it weighted by capacity or by generation?
It's weighted by the generation.
Okay. Let me see about questions. Everyone, please use the Q&A little tab on the top or somewhere in your screen to post your questions. While we wait for those to come in, I have a question about the US more specifically.
Okay.
And so for the US, so for developing countries and at the national levels, like I understand, you have to use like aggregate emissions for the whole country. For the US, you try to go down to the state level. And I was wondering, like there's, like, the power system is not at the state level. And so you mentioned California is doing, for example, a lot of renewables. So like the transmission and distribution losses maybe are not as important in terms of mitigation of emissions, are not as important in California, but California is still importing. I think it's decreasing significantly, but there's still, I mean, historically they imported a lot of coal generation from other parts in the West through long distance transmissions. And so I was wondering, how do you account in your state results, how do you account for electricity flows across states through like because you have the ISOs or the RTOs and transmission losses that may occur. So in PJM, for example, most of the coal plants are in the western part, and the power flows to the eastern part. And so transmission distances there are a bit longer. And so you may be losing more power from the coal power plants than from the plants that are more locally. I was wondering if you thought.
Okay, so I completely agree that you can't just like bound it at the state level. So this kind of backup slide is my attempt at getting at the ISO level. And so we've taken like the kind of ISO bounds, and I got this one from like it's a geospatial data set. I can look up the name if you need it. And so like we're using this to look at the transmission and distribution losses within the ISOs and so how that compares for different ones. So, like we saw like California and Texas having like really high level of losses, but then when we were looking at the ISO level, we actually saw like MISO was having high level losses. Now that's just, one of it's just because of their size. And then PJM is also pretty high up there with CAISO. One of the challenges is that it doesn't take into account the Southwest power pool, so Florida was a little high up there. But the plan for the analysis going forward is to do like the national US level, look at the ISO level, the state level, and the specific power plant level. That way we can actually see like how would our policy recommendations change at these three different levels.
Okay, so I have other questions, but let's go to some of the ones that are coming in. Okay. I think I'll start with one that is more specific to transmission. And so the question is, can you comment on country size and voltage level, if you have that information, considering longer transmission lines results in higher losses if the voltage is low? So I think maybe that question is a little related to what I describe with longer distance and then voltage also being important.
Yeah, so I actually don't have the information on voltage level of different countries or like what voltage level they're at. I could look that up, but I don't have that in my analysis.
Okay. So one of the other questions that's come in, so I'll just read it. They're thanking you for the interesting presentation, and they're wondering if you have any thoughts about how reducing transmission and distribution losses compares to reducing consumer demand as a ways to reduce emissions. as both methods would reduce generation from power plants. And so have you thought about doing a comparison, I guess, and looking at the economic and/or challenges for implementation?
So I think that kind of my thought process on that so far has been to think about like reducing the non-technical losses. So there are some like kind of like stealing, pilferage, etc. And so that actually is slightly different because you can't just do like energy efficiency for that. You could use smart meters to help to reduce the like probability of theft, but also that kind of just hinders people from planning the grid properly. Now, the consumer side, I haven't really touched the efficiency or demand side management of that because I do think that, I mean, it's just a different question. At the beginning, I showed like, you know, there's the power plant level, the T&D level, and the consumer level. And I haven't looked at the like ability to reduce demand from like efficiency of appliances. I think that in a lot of the developing world right now, they are trying to increase their energy usage. And so then, you know, it would be a little bit harder to kind of do the country comparison as well, because so many countries are just trying right now to just increase their usage.
So I guess I have a question maybe related to that. So, right, like cost effectiveness is a really important metric in all of these analyses. Typically, I mean, CO2 is easy. We just looked at dollar per ton of abatement, but you could do something similar for the other emission factors. And I was wondering if you thought about, like, what are the strategies that could lead to these emissions reductions by reducing transmission and distributions, and how there is cost, like the cost effectiveness. And I'm thinking out loud here, but there's an example of, right, so in MISO, you're putting in a lot of wind also in the west, and it serves load centers in the east. And if you have a lot of losses from that wind, you're not using the resource as well, and you have to compensate for it through other resources that can be fossil resources. And so if like the cost effectiveness, first, if you can use the wind resources more effectively and reduce emissions, like first of all, what is the avoided cost of having to build new capacity compared to the cost of improving the transmission and the strategies? And are there different strategies to improving or reducing transmission and distribution losses?
Yeah, so I think that I would need a slightly different model to kind of answer that question. So one of the thoughts that I have on that one are kind of like, what's the value of upgrading certain lines? Because, you know, the transmission distribution system is so complex and so vast that, you know, having one line upgraded to reduce the congestion or help free up the flow of electrons could actually then link two major parts of your system and like allow you to send a lot more from wind, for example. And so that one you're going to have to kind of model actually at the like, I think the like a power, like a IEEE bus, I'm kind of imagining an IEEE bus model to actually see like, well, how much electrons are being held up and like which line is going to be the most cost effective and how much is that going to cost you? And then what's that cost compared to just building more solar sites or more wind farms closer to your actual consumer demand?
So interestingly, one of the questions that came in, I guess, as I was speaking, is similar. So the answer you gave might help with this, but I'm gonna read it anyway, because actually Brian may have more eloquently asked the question. So he says, I am curious about the cost implications of losses when it comes to resource planning, particularly for more aggressive RPS programs in the US. Have you thought about, or are you aware of any work that weighs the potential cost of having to build excess capacity due to losses versus the cost of the actual investments to reduce technical losses? I imagine both would have significant impact to retail customers. Curious which you think is more significant. So I think it's better, same question, but better articulated.
Yeah, so I think that like if you look at my collaborators' work, so Kavita Serrano and Sarah Jordan, their work that I'm building on, so their CO2 emissions work actually was looking at like the cost of the different investment strategies and kind of like how much that would cost. I don't know if they did the exact trade-offs, but there are papers in Nature Climate Change, and I can actually the citations right here. It's the third one on my key references. When I'm thinking about like evaluating the cost, I think it's going to be very country and region specific as well, because you know the cost to invest in different generation sources, depending on the incentives, and then the space and the land and the resources are going to vary by country, by region. And so we are going to try to incorporate a cost metric in here, but I definitely need to think it through a little bit more.
Okay. Let me see. So one of the other questions, I'm gonna just read it again because they put it better than I can say it. So thank you for the presentation. Not sure if you described this since I joined a bit late. Could you provide more information about the correlation about grid and transmission efficiency versus the type of fuel used for generation? So for example, how does grid efficiency vary if you have more renewable versus more core fossil fuel based generation?
Okay, so I'm assuming that this is like how it varies by countries with coal-based grid versus renewable-based grids? Maybe. Okay.
I think maybe like they're wondering if there's a correlation between the fuel type used for the generation and the transmission losses associated with that generation.
Okay.
Regardless of the country, I guess.
Regardless of the country. Okay. So I think my most helpful graph would have been this one. So I didn't break up the countries by fuel type dominance in this work. Now, this is the picture of, this graph was the picture of the transmission and distribution loss percentages along the X and the emissions from electricity generation along the Y. So, of course, the more oil-based and coal-based, the more oil-based and coal-based systems are going to be closer to the top, right? The more fossil fuel-based systems are going to be closer to the top. And so, I mean, there is kind of like some decrease, but I would have to, like, I couldn't say that this is just solely going to be based on the type either, because this is also including like the actual level of generation, right? So Iraq, for example, might be very coal-based, but they just might not generate as much as the US and China. So I would have to kind of tease that out and get back to whoever asked the question.
Perhaps do you mind if I try to clarify something with that question?
Yeah.
Okay. I mean, I guess like an electron is an electron regardless of how it's generated. So unless there's a like geographic, like spatial correlation between the type of resource and the voltage and the distance of the transmission, like if you have a coal power plant in one location and a wind plant in that same location so that the transmission system is the same distance, the same voltage, like the losses would not be correlated, would be the same whether it's generated with coal or wind. The correlation may come in by resource type if all of the wind is far from the load centers. And so you may see that the transmission losses for wind power, power generated with wind are higher than power generated with coal. But I don't think there's anything that is specific to the generation technology itself, more about where the resource might be. That's my thought. But maybe if anyone else has comments on that, it will be. So another questions, and I think I'm going to merge them in two, is can you think of transmission losses within the states For example, how would different parts of upstate or downstate New York differ, or the top of Michigan where there are historically serious transmission constraints, or some parts of the West are electrically California, like Utah. So like a lot of the generation in Utah is actually going to California.
So when I'm thinking about the losses within states, like I wouldn't want to go too much farther down than the state level, because it is hard to know where an electron has began and ended, especially because like, so going back to the kind of the ISO level, you know, there are connections between these ISOs, and, you know, electrons starting kind of in the southern tip might translate to the middle. So it's not going to stop within the state. At the state level, I was focusing on the state level partially because of like state energy policies, and thinking about where are we making policies, at what levels are we going to be making policies. Now, if I was going to kind of think about wanting to have a more targeted policy, not at the state level, then I think that that's when we would kind of focus on compensatory generation. So like this graphic is kind of an image of just all of the power plants in the US. And then if we actually think about how that translates to emissions in this map, then you're going to see that some power plants just rise to the top in terms of average emissions. Now, so, you know, while this power plant, I mean, this power plant is pretty huge down here in like Georgia area, and I'm not sure exactly like where the electrons are going. So if I had a state policy, then maybe they would want to retire this power plant. If we had the ISO policy, then maybe we're kind of looking more at kind of reducing the losses within our system in combination with retiring certain types of power plants.
So I guess to follow on that, I know, for example, in ERCOT, you can get data by load zone, and similarly in CERC in the Southeast, I think there are 4 load zones, and you can get some information about transmission constraints and maybe even transmission losses between load zones or between transmission zones. So that might be if you instead disaggregate the country in terms of like, rather than by the whole ISO or by state, you look at transmission zones and then try to identify if you can get transmission specific losses for the flows from those zones. And then you have the emission factors based on the generation within that zone. You could do something where you're disaggregating a little bit more and characterizing like the different resources and where they are. So that's just an idea.
Okay.
So I think I don't see any more questions, unanswered questions, and we're already a little bit close to the hour. So I think
can I ask one question? This
yeah.
was really great. And then I know you want to, but one of the things that I was really curious about was if you had to tell utility or policy people kind of 2 things to do to really address this issue, what would you focus on, Destenie?
So I would focus on telling them that we need to focus on the co-benefits of our energy policies. And so it's not solely about the generation, it's about doing the combination of generation and transmission infrastructure investments. So we want to make sure that if we're going to invest in all this wind, we can get all of those electrons to as many people as possible. And then also, you know, when we're doing decarbonization of our grids, we want to also remember to also incentivize reducing air pollutants, because those localized air pollutants will also have adverse health effects. And, you know, reducing CO2 doesn't always translate into the same pollutants, like they're slightly different targets.
And when you showed those like hair knots of you know, distribution wires,
I'm assuming like this.
I hadn't appreciated, yeah, exactly. I hadn't appreciated how the losses were so large in some parts of the world. And are there kind of, you know, and you mentioned the technical, non-technical, is there like an average split, like 50% non-technical, or I mean, are there ways that you kind of rule of thumb think about that?
So disaggregating those is actually pretty difficult.
Yeah.
You know, people don't often want you to know when they're stealing electricity or when they're, you know, not being charged enough for their electricity bills. And so sometimes in some countries, you'll see the wires like this because people kind of like pretend like they're in electricity and hook up the wire themselves, right? And so the electric company then has to kind of go figure out like what's the actual installed wire, you know, what's kind of a legal connection, right? There's also some safety risks associated with these. So it is very difficult to disaggregate those losses because if there was like a direct number where you could pinpoint how those losses varied even within those countries, then the electric company would probably go and like remove all of those extra lines and actually reduce those losses themselves.
Thank you for those insights. And then
so Destiny, I think this is great work. I actually can see like three different papers coming out of this work. But to wrap up, I was wondering if you have any thoughts about like broader issues and where you see the work moving, this work or any other work that you're passionate about, where you're taking it.
So I guess that where this work I see going, like I really do want to look at like the cost of investing in T&D versus the cost of like building generation. So kind of combining my previous work and this work. In addition, for like in developing countries, there's a lot of push for reaching Sustainable Development Goal 7. We want to have like universal access. And so then for me, my big kind of question is like, what should that access look like? And so I'm really interested in like, you know, how do we reduce like the theft, but also like, how do we just plan our systems better so people don't feel the need to steal? So I may be building systems to account for productive uses of electricity, like agricultural production or like business electrification. This might also mean like deploying smart meters. And so kind of, I like energy modeling. I'm an energy modeler. And so I'm really interested in like kind of open source, large scale models.
Great, thanks. I think Elizabeth, we go back to you now.
Well, I really want to thank you, Destiny, for your participation in this series. And you know, again, we ask everybody to send in your ideas for future speakers, but really thinking about the T&D questions is one that a lot of people really gloss over. So I really appreciate your, you know, shining a light on that important topic. People like to talk about generation and people like to talk about use, but this how it fits together ends up being so important. And I think you really highlighted that in important ways. One of the things that we aspire to do in the speaker series is really to highlight the work of young scholars like Destiny. And we have a bunch of different events kind of coming up. Stephanie, could you share those with us? So next on August 26th, Jesse Jenkins from Princeton will be talking about clean energy, clean electricity, linchpin to a net zero economy. And then after that, we have Erin Mayfield. We're still waiting for her talk title. I sent around another reminder email. Hopefully we'll hear soon. But again, everybody, thank you so much for participating in these events, and feel free to share the archive talks with colleagues and friends. And we look forward to continuing these conversations in the future. Thanks again, everybody.
Thank you.
Bye.